Welcome back to Mr. T's third installment for gas laws. So, you know what Mr. T says? I pity the fool who's got to sit through 3 of these discussions. That Mr. T, me, Mr. T, you know, pretty close. Anyway, Gay-Lussac's law is the third installment. We have 2 variables when dealing with Gay-Lussac's law. One is pressure, the other is temperature. We're going to hold 2 things constant: volume and number of particles. So where might this come up? Well, it could come up in your everyday aerosol can. Spray paint, maybe some of you, your parents, mom probably uses hairspray. If it's in a metal can, this type of aerosol can. The volume is going to be held constant because it's metal, can't change. The number of particles, even if it's empty, there's still some gas in there. So the particles can't change unless you hit the spray part of it. Now, let's say we change the temperature. So when I was growing up, we used to have a burn pile in the back in my grandpa's farm, and we'd get rid of the garbage that way before we had curbside pickup. So my mom had a metal hairspray can. So if you throw that can in, the volume can't change, the number of particles are being held constant, but the temperature is going up quickly. Well, think about what's happening inside it. As the temperature goes up quickly, the number of particles in there doesn't change, but they're moving faster. What did we learn about with KMT? Faster they move, more collisions means more pressure. So the pressure inside the can is going up quickly. Well, that's a direct relationship. When one variable goes up, the other goes up. One goes down, the other goes down. You should have a graph or a chart that looks like this if you would chart it. Well, with that in an aerosol can, so you got an aerosol can heat, the pressure's going up steep, what's going to happen eventually? You got it. Yeah, it's going to look something like that. So you need to be a long ways away. What I'm basically getting at is aerosol cans and temperatures. It's an example of what could happen, very dangerous. So obviously you don't want to put aerosol cans into burn cans, stuff like that. People can get hurt, lose some fingers, appendages, stuff like that. Since it is a direct relationship, the formula is going to be division. So you have initial pressure divided by initial temperature, secondary pressure divided by second temperature. And it still needs to be in kelvins. Okay, so we have to use our kelvins where we add 273 degrees to whatever Celsius we have. So let's do a practice problem. So for Gay-Lussac's, I'm going to go over the board here and I'll walk you through. Same thing like we did in the other ones. First thing is we'll read our problem. Second thing, we're going to make our list. So, gas has a pressure of 250 millimeters of mercury. There's P1. Now that's a new pressure unit that we haven't seen yet. But like we talked about earlier, we're going to go through those 3 different types of units in class. At 200 degrees Celsius, so we have T1, 200 degrees Celsius. What will be the pressure? So there's P2. X. Now they didn't tell us any units, so I'm not going to be picky and put them down. At 20 degrees Celsius. So we have our secondary temperature, 20 degrees Celsius. So we made our list. Let's check it twice. Kind of like Santa Claus. Is our units of pressure the same? Well, X, I'm going to leave it in millimeters of mercury because the problem didn't ask me to change it, so I'm not going to create extra work for myself. Temperature, Celsius, Celsius. The same, but remember our gas laws, we have to convert to Kelvin. So I'm going to add 273, which makes P1 473 degrees Kelvin. Add 273, which makes T2 293 degrees Kelvin. Now let's do some work ahead. We talked about this as a direct relationship. Our temperature goes from 473 to 293. Temperature goes down. So what should we anticipate our pressure doing? It should also go down, direct relationship. So we should get something less than 253. Let's work this out. We'll plug those numbers in to our formula. P1 over T1 equals P2 over T2. And then plug the work in, the numbers we had there in our list, as it plugs in. P1 winds up being 250 millimeters of mercury divided divided by 473 degrees Kelvin equal P2 divided by 293 degrees Kelvin. I know I'm working off the board here a little bit, but you can still hear me. How do I get, you got to isolate this on the same level. I'm going to cross multiply. So if I walk over here, I'm going to wind up with P2 times 473 Kelvin equals 250 millimeters of mercury times 293 degrees Kelvin. Got it all on the same level. Let's isolate for P. 473 Kelvin cancels out. 473, do the same thing to both sides. 250 times 293 divided by 473, we should come up with an answer of about 154.9 millimeters of mercury for our pressure. We go along with it, temperature decrease, so did our pressure.